So that's why in the advent of horizontal drilling, down in the Barnett shales, over the last 15 to 20 years, the concept of horizontal drilling really came into maturity, where you sink a vertical shaft, then over about a quarter mile to a half a mile, make your turn, and extend out, right now, as far as 2 miles. And then subsequently go back to some wonderful videos on YouTube and stuff like that about the hydrofracturing process, animations. But basically, once you have your drilled bore and you've cased it, grouted it, then you go back in and you hydrofrac at intervals which currently in Pennsylvania are on the order of about 500 feet. So you'll have multiple hydrofrac zones along that lateral from which you'll be extracting your gas. And you need to hold those cracks open. That's why we use proppants. And each one of those hydrofracts is on the order of 100 tons of material. All right? So think of 4 to 5 coal trucks, triaxles, of this material per hydrofrac. Give you an idea of the kind of truck traffic you need just to service one lateral. Not to mention the fact that lateral is good for about 6 to 8 million gallons of hydrofracturing fluid, water. Right? So this is an enormous deal. This is much bigger than we scientists working with that. Okay? What's the driver? Big market. New emerging natural gas play. Conventional raw materials. Going through a huge price increase. Number one, because our best bauxite reserves are under increasing pressure. Bauxite's used for making aluminum, okay? As well as other earthenware type ceramics. So hydrofracturing and propping is not its sole market, but could become the biggest draw on it. To give you an idea, bauxite went from about $150 a ton to over $900 a ton over the course of 4 years. You have to buy proppants, you have to make and sell proppants in the range of $500 a ton for it to be economically viable with technology from a couple years ago. That's why this is a huge driver. So we've concentrated in recent years, we switched our work from bauxites and zircons to alternative raw materials which are closer to the site of application and which are cheap. Okay, so they're nearby, your transportation costs are low. They're typically being sent to landfill because they're either recycled materials, mine tailings, or drill cuttings. And therefore, you're using them in the area where you need them, manufacturing them into proppants. You have all the green arguments, you have your transportation arguments, you have your cost issues on raw materials, and it's pretty doggone nice if we could make Pennsylvania be a bigger player than other than being the source of the natural gas. We have a huge manufacturing infrastructure in Pennsylvania that is the refractories and steel industry that probably we could use some of the excess manufacturing capacity to meet this demand. That is what we have proposed to do and that we're currently funded to do. The cost per well can be big. We're talking large numbers. Okay? So as a faculty member who goes out and busts their butt to get $125,000, $150,000 a year per project to run a graduate student, when we hear that they're using $3 million a well, 1,000 wells a year, it gets our attention. Okay? So, what have we done? Let's get to the research now. I'm going to tell you about 3 different areas of research that we're doing. The first is in conventional state-of-the-art proppants that are bauxite or kaolin derived, right? What can we do to either use a lower grade ore? What can we do with our processing, time, temperature, etc., in manufacturing these things to make them useful, manufacturing them from ores that typically wouldn't have been used in the past? I'll tell you a bit about that. What can we do in terms of using non-traditional raw materials? Mixed glass cullet from the domestic recycling stream, mine tailings, drill cuttings, all of which are landfilled. Okay? What can we do in terms of either one of these via processing, come up with the right compositions and microstructures which give us the mechanical properties and the corrosion behavior and specific gravities that make these useful as proppants. That's where our research has been focused for the past 15 years, but over the last 5 years or so, more in this arena. We're interested in industrial and domestic waste streams that we're paying to put into landfill, but that could have a value added as a raw material. Okay? So, let me tell you about the first piece of work. What you're looking at here is photographs of microstructures of a bauxite-derived proppant, where we changed the classic, for a ceramist, the classic processing parameters of heating temperature, time at soak temperature, percent drain, and heating rate. To give you an idea how these are made, state-of-the-art proppants are made by aggregating powders into little snowballs using like an IRIC mixer or what have you, and then introducing them into what is akin to a large ceramic kiln or cement kiln, large rotary furnace tube, scale of these things being 15, 20 feet diameter, 60 feet long, cooking at about 1600 degrees centigrade at the hot end. Right, so over 3000 F. Fuel fired, typically fuel oil, sometimes natural gas. Putting the material through that, and in the course of time, as this thing rotates, it has a certain residence time until what comes out the end is a hot particle, many, many, many of them, tons per hour, right, that have been sintered to give a certain microstructure, density, and mechanical property. All right? That's the current process for manufacturing these. This is all technology that's been around the ceramics and cement community for 100 years. Okay? Well, what we were interested in knowing was, okay, given a certain ore, bauxite ore, is there something we can do to tailor microstructure and to tailor chemistry via changing the time at temperature during the sintering process to give you better properties? So we spent about 5 years working on that. And what we were able to demonstrate was that what the proppant community hadn't looked at, but the refractories industry did for years, was that issues, all the phase equilibria related to steel refractory slag interactions plays a role here. All the work Arnulf Moine and Albert Osborne did at Penn State Geosciences is pertinent here. We have to have the right crystalline phase assemblage. Cristobalite, a polymorphosilica, is a bad actor insofar as mechanical properties. You have to follow the crystalline phase assemblage evolution, the microstructural evolution, the density evolution, and all of these have a complex interrelationship on determining mechanical strengths. And what we found, and what this is showing now, is from rather mundane sort of sintering temperatures and times. You're talking mundane being 1450 degrees C sort of range. That's the lower end. To over 1600 degrees C out this way. All right, heating rates from a few degrees Fahrenheit per minute to 20, 40 sort of Fahrenheit per minute, degrees Fahrenheit per minute. So that's throughput through your cement kiln, okay? We found that we could get microstructural evolution. These are large grains of, in this case, mullite forming, and the other phase there is glass, an aluminosilicate glass, very common. That's a classic ceramic earthenware, right, Steve? Okay? And what we found was that we could have a sweet spot where we had very rapid heating rates at markedly lower temperatures for relatively short times, gave us a better or comparable product to the stuff they were cooking the bejesus out of. And the reason for it was we played with the kinetics of the cristobalite evolution. Okay? Or consumption, as it turned out. Well, that allowed this company to make more product faster at a lower temperature. Use less fuel, less time. Everything's there for you, right? Yeah, well that's good. Bauxite did the same thing with kaolin, all right? That was a master's thesis. All right, and then we subsequently said, you know what? We know something about liquid phase sintering. We're ceramists. These are liquid phase sintered. If we modify the glass phase chemistry so that we modify its viscosity and melting temperature, softening temperatures and the like, as well as the activity of different species in that glass, we can accelerate that sintering and accelerate the evolution of desirable phases and the removal of undesirable phases like cristobalite. And the way you do that is through a concept that ceramists and geochemists and so on would call doping. Okay? You modify the chemistry of that glass phase by adding things. Now, the ceramists and the crowd are going to sit here and say, you're nuts. Sure, we know that. What are you going to put in there to make it go better? We're going to put in alkali and we're going to put in iron. Why'd you choose those? Because we went to Arnulf Wand's phase diagrams and we said, the steel industry says that if you have this in your refractory, you're going to have these kinds of reactions that, for the purposes of refractory, are undesirable, but for the purposes of densification by a liquid phase, are everything you want. And you add an additional process parameter, 2 of them, composition of your dopant, how much you put in, and what your oxygen partial pressure is while you're sintering these things, give you different microstructures. Okay? Wasn't sexy enough for the ceramics community. I gave this talk 15 years ago, a form of it, at a ceramic society meeting to about 1/3 of the crowd that's here. All right? There is no ceramic in the world that's going to be made in the quantity that proppants are going to be made in next year. Nothing. I don't care if it's a semiconductor. We know it's not a quantum dot, and it sure as heck isn't a nanocrystalline biomedical device. 20 billion pounds per year. Okay, it should get your attention. All right, so what we did, we said, let's dope this stuff. We want to promote or modify the presence of how much liquid phase we have during sintering. This is geochemistry at its best. All right, it's lava. Okay? We want to increase the mullite content. Mullite is an aluminosilicate, 3 aluminas, 2 silicas, that has a very desirable effect on strength because it gives us acicular crystals in the microstructure, and they're very, very, very creep resistant, potentially very strong when they're made by liquid phase sintering process because they're largely defect free. We want that stuff. There's the mechanical aspects of the ceramic world. Okay? Potassium was one of our dopants because it's an alkali oxide. Okay? Alkaline oxide. Basically, what it does is it lowers the viscosity of the glass phase during sintering. So my solution precipitation processes and my particle rearrangement happen fast. I can sinter faster, and I can suppress the evolution of certain phases that happen at the latter ends of your sintering run. Okay? This is what we do as ceramists. Right. We also looked at iron oxide. I think that's on the next slide. Iron oxide, why? Iron has several different valences. You sat through Stubbe's course. Do you remember the iron oxide phase diagram and the isobars and the experiment that Tressler made you do in your thermal treatment lab where you made an iron oxide pellet and you put it in a gas-fired furnace and you heated it up and you changed the PO2 and all of a sudden it went into a puddle? Changing the valence of the iron in an iron oxide alters its melting point. Number 1. Number 2, changing the valence of iron in an iron oxide as a dopant in an aluminosilicate changes the viscosity of the glass that you get. Number 3, by changing the valence of the iron in an iron oxide dopant, you can tailor which of the crystalline phases you would expect to be at equilibrium after the sintering is done in a mixture. And the types of dopants we're using would give us equilibrium concentrations over here. But the fact is we're throwing a lot of, in a localized fashion, iron. We're down at this end of the phase diagram. We've suppressed the melting points of the other more refractory phases during the liquid phase sintering process by using non-equilibrium thermodynamics to our advantage. Okay?